Hey everyone. So today we're going to pull back the curtain on artificial intelligence. We're going to look right at the engine that makes it all tick, the math. Seriously. We're going to demystify the core ideas that let a machine actually learn, see, and, understand our world. So it all kicks off with a pretty simple question. You and I, we look at this and we instantly know it's a zero. No problem. But a computer? It doesn't see a drawing. It just sees a grid, a big block of numbers. So how in the world does it get from that sea of data to a confident answer, yep, that's a zero? Well, that's the journey we're about to go on. You see, for a machine, every single pixel in this image is just a number. It's a value that represents how bright that little dot is. The whole image is basically just a giant spreadsheet of grayscale values. It has zero inherent meaning. And that right there, that's the fundamental challenge. How do you translate our rich visual world into a language that a computer can actually work with? And the only tool we really have for that translation, it's math. Math gives us the rules, the structure, and the language to let a machine find patterns, to make sense of all this complexity, and at the end of the day, to learn. It is the bridge between how we see the world and how a machine computes it. Okay, so that brings us to our first major step, representation. How do we take something kind of messy, like a hand-drawn doodle, and give it a clean mathematical structure it can understand? Well, first, we just break it down. An image is really nothing more than a grid of tiny little squares, right? We call them pixels. And we can give each pixel a number, let's say 0 for pure black, 1 for pure white, and all the shades of gray get a number in between. All of a sudden, our picture isn't a picture anymore. It's a structured grid of numbers. Now, the next step sounds almost too simple, but it's incredibly important. We take that two-dimensional grid of numbers and we just unroll it. We go row by row and lay them out into one single super long list. So our 28 by 28 pixel image, it just became a list of 784 numbers, one after the other. And this long list of numbers has a very powerful name in mathematics. It's called a vector. Now try to think of it as a single point, but in a really, really high-dimensional space. And what's so cool is that this idea is totally universal. It's not just for images. An audio clip, a sentence, even your company's financial report, anything that can be turned into an ordered list of numbers can be a vector. Okay, so our image is now a single point, a vector, living in some crazy 784-dimensional space. And we've got thousands of these points, one for every single drawing of a handwritten digit we have. So now what? How do we actually find the patterns in all of this? This is where matrices come into the picture. As the source material puts it, matrices are way more than just grids of numbers. They're operators. They represent things called linear functions, which is just a fancy way of saying they perform predictable actions on our data, like stretching, squashing, or rotating it. Honestly, the best way to think about a matrix is as an action verb for our data. When we multiply our vector by a matrix, we're not just getting a new vector back out. We are fundamentally changing the entire space where all of our data points live. A matrix can literally stretch that space out, squash it down, or rotate the whole thing around. And each one of these transformations gives an algorithm a new way to look at the data, right? Stretching might emphasize the features that really matter. Squashing could get rid of irrelevant noise. And projection? Well, projection can collapse thousands of dimensions down to just a handful, which helps us see the hidden structure underneath it all. A classic example of this in the real world is a technique called principal component analysis, or PCA. It uses these exact matrix transformations to automatically find the directions, or axes, in that high-dimensional space where the data is most spread out. And why do we care about that? Because the directions with the most variation are usually the ones that capture the most important features, the things that separate a 1 from a 7 or a 0 from an 8. It's how the machine figures out what's signal and what's noise. So let's bring it back to our digit. PCA can look at thousands of different vectors that are all supposed to be a 0, and by doing a series of these rotations and projections, it can figure out the essential combination of pixels that really defines what a 0 is, and it can separate that from all the little quirks and variations in people's handwriting. So we can turn data into vectors, and we can use matrices to transform them and find patterns. But how does a model actually learn? Well, the simple answer is that it learns by being wrong, over and over, and then systematically correcting its own mistakes. The source material gives us this perfect analogy for this. It's like climbing a hill, except, and this is the important part, we're not trying to get to the top of the hill. We're trying to find the absolute lowest point in the valley. Imagine a landscape where your altitude, your height at any given point, represents how wrong the model's guess is. The goal is to find the deepest part of that valley. This whole process is a really elegant loop called gradient descent. The model makes a guess, then it measures how wrong it was, that's the error. Then, using a bit of calculus, it figures out which direction is the steepest way downhill to reduce that error, and it takes a tiny step in that direction. And then it repeats the whole thing, thousands, sometimes millions of times. Guess, measure, step. Guess, measure, step. And with every single loop, it gets a little bit closer to the lowest possible error. That is learning in action. All right, so let's zoom out and just recap the entire journey our simple drawing of a zero has taken us on, from being just a picture on a screen to an actual prediction. We started with representation, right? We turned a picture into a vector, a point in space. Then came transformation, where we use matrices to manipulate that space to find hidden patterns. And finally, we had learning, where the model used optimization to get better and better by constantly minimizing its mistakes. And really, that's the big takeaway here. Whether we're talking about recognizing a face, translating a language, or even driving a car, this fundamental trio of ideas from linear algebra and calculus, representation, transformation, and optimization, this is the mathematical engine powering pretty much all of modern machine learning. You know, what begins with something as simple as turning a drawing into a list of numbers, it opens up this incredible world of possibilities. It's not magic, not at all. It's just math. But by teaching machines this language, we've enabled a whole new kind of intelligence. And I guess the only question left is, what conversations are we going to have with it next? Thanks for watching.